All right, so today what I'm going to do is show a technique for asking if an interaction can be rescaled to parallelism. I put another way, we're going to ask if an interaction might be due to a nonlinear response scale. Put another way, we're going to ask if we have a set of data that are not parallel when graphed up, can we find a way to make them parallel so that they fit an additive model? So here are some data to illustrate it. These are data from a paper I wrote or I published in 1974 on the additivity of personality impressions, a test of a theory that the amount that you like a person who's described by two adjectives is either the sum or a constant weighted average of the likableness of the adjectives. So the theory is each adjective has a value, and the value of a combination of adjectives that describe a person is an average of the two component values, or the sum. In this case, because there's always exactly two adjectives in each person, the additive model and the averaging model make equivalent predictions. So we're going to phrase this as an additive model, and we're testing for additivity. When we do the experiment, we get these values. These are the mean ratings. There were three groups of 100 subjects each who did the experiment. The experiment was replicated with different sets of adjectives, and the adjectives were chosen from a list of adjectives that had previously been scaled according to likableness. And so people were asked, how much would you like a person who's malicious? How much would you like a person who's blunt? How much would you like a person who's practical? And so each adjective was rated, and the adjectives were selected equally spaced along the rating scale from low, in other words, low values of likableness, medium negative, neutral, medium positive, and high from this previously scaled list. And then adjectives were paired in a factorial design. So one set of adjectives might be words like malicious and unaccommodating, blunt, practical, intelligent. And you might have words over here like phony, noisy, and words like that up to, say, sincere. And so one set of adjectives might be paired with a different set of adjectives. And this might be, how much would you like somebody who's malicious and phony? And over here we might have, how much would you like somebody who's sincere and intelligent? And so we've got combinations, and these are the ratings that were obtained from three different experiments with different sets of adjectives. And they've been averaged together here to give us some data we could work with. Here's what they look like when they're graphed. Instead of being parallel and showing the implications of an additive model, which should be that the slopes should be the same, but instead this slope, if a person has one bad adjective, it doesn't matter so much what the other adjective is, as if the first adjective is, so this is all where it's L combined with L, on up to L combined with H. But if the first adjective is positive, well, then the same second adjective has a much bigger effect. Or phrased another way, the gaps between the curves, if one adjective is L, the vertical spacing between the curves should be the same under an additive model, but it's less over here if one adjective is dislikable, is low in likableness, than it is if the adjective is high in likableness. So we get this kind of divergent pattern, and we're asking, could these data have arisen from an additive model with a nonlinear response transformation? And so in order to do that, in the old days, we used to use programs like Monanova, which implemented, that was a program written by Kruskal and Carmone, and it took the data and tried to find a monotonic transformation that would make them parallel. This technique is slightly different, but it basically amounts to the same thing, the technique I'm going to show. So we're going to take the data matrix and I'm going to copy them down here. And I'm going to create a theory matrix corresponding to the data matrix where we try to put values on things. So over here, we've got the data. And over here, we're going to have a matrix of theory. And I'm going to just start with some numbers that are ordinal, but we're going to try to solve for better values. So 1, 2, 3, 4, and 5. And 1, 2, 3, 4, and 5. So we're going to say, we're going to start off with the idea that these might be the values. And I'm going to color them in yellow just to show that these are going to be the parameters that we're going to solve for. And the basic idea is what we're trying to do is we're trying to see, are there numbers instead of 1, 2, 3, 4, and 5, but maybe some other numbers that we can find? Can we find some numbers such that the sum of these two numbers produces the same rank order as the data? In other words, can we find a theory that is monotonically related to our data? And the technique we're going to use is to rank order the data and rank order the theory, compute the correlation between the two, which amounts to the Spearman rank order correlation. And we're going to try to maximize that Spearman rank order correlation using the solver in Excel. So we're going to we're going to name these values in Excel, the 1, 2, 3, 4, and 5. These are the row scale values, but in this case, the data matrix is symmetric. So we really only have one set of scale values. I'm going to make these values equal to these, but I'm going to write it more generally to begin with. So we're going to label these, or we're going to assign these the name by naming them over here in the naming box. So I've selected 1 through 5. I've clicked over in the naming box, and I'm going to call this row underscore. And I hit return, and that gives these cells that are highlighted in yellow here, it gives them the name row. And I'm going to call these the columns, or we'll call it column. Click over here, we'll say COL and an underscore. And the reason I add an underscore is sometimes combinations, like you might want to call something A sub 1 or A1 or A2, but those actually are cell numbers, A1. So to avoid getting yourself confused, I always add nowadays a underscore to prevent myself or my students from getting mixed up by contradicting cell values in Excel. Okay, so we've got something called row and something called column, and we can create a theory matrix by typing here equals row underscore plus column underscore. And when I hit return, that fills in the values. So here are the numbers. Here are numbers that are perfectly additive. And these numbers have the property that the slope is the same. This goes from 2 to 6 going this way, which is a gap of 4. And from 6 to 10, that's also a gap of 4. And because it's symmetric right now, it's going to do the same thing. We're gonna then solve for these values that are in yellow. I'm going to constrain the columns also to be equal to the rows, and we're going to use the solver to maximize the Spearman correlation between the theory and the data to see if we can find a set of numbers such that the sum of the numbers reproduces the rank order of the sum of these numbers reproduces the rank order of the data. Well, it doesn't do so right now, because we know that these data are parallel over here and these data over here have that interaction. So we're going to find now the ranks of the data, and we'll put them here. Ranks, like a plural. And by rank, I'm going to rank, what I mean, I'm going to rank from, we can copy this down here. What I mean by the ranks of the data is we're going to just number them from the smallest number up to the highest number, and we're going to call the smallest number 1 and the highest number, well, there are 25 numbers here. We'll call this largest number, number 25. And we're going to, if the things are equal and we see we have some tied values, we'll just give them the average of the two ranks. So we're going to use the rank function that's in Excel, where if two things are equal, they get the average of the two ranks. So we notice that the smallest number here is 1, and the next smallest number are these two values here that are equal. So these are 2 and 3, so we're going to average the two, make them 2.5. This will be rank 1, and this will be 2.5, because it'll be the ranks of 2 and 3. So we're going to say this is equal to the rank of, and now we're going to have this be the rank of this number, and I have to type a comma right here, and then I select the cells, the range of values that it should be compared to. And it'll be these 25 numbers between C18 and G22. So I'm going to use the dollar signs so that it won't move when I change the other values. So it'll be between dollar sign C, dollar sign 18, colon, dollar sign G, dollar sign 22. And then the rank function wants to know if you're going to go ascending or descending. And in this case, we're going to be ascending. So that'll be, in other words, the monotonic transformation between the data and the ranks is in the same direction. It's monotonically increasing. And so ascending in this case means monotonically increasing. And I'll finish the paren. And this gives me the rank. And so the 1.54 has the rank of 1. It's the smallest number compared to these 25 numbers. And then I'll use autofill to fill in the rest of this matrix. I get the little plus in the corner, and I drag it across, and I get the ranks. And it goes from 1 to 25. And let me see what I did. I just have the regular old rank function here. So it skipped ranks. I didn't do the rank average, did I? So I'm going to fix that. I'm going to type rank. Let's put that back in here as rank.avg. And that's the function that'll average the, so that's still 1. And now we're having those 0.5s are averaged, and we get to 25. So there's the rank, using the rank average function. So rank.avg is a function that'll, when two things are equal, it'll say, oh, these are ranks 2 and 3, and then give you 2.5 for them. So the ranks of the 2.1s are coming out as 2.5 here. And we want to do the same thing with the theory. So we're going to have ranks of the theory, and we're going to corresponding to our values, we can rank the 2, which is the sum of the row and column values, relative to the 25 entries in the theory matrix. So we're going to do the same thing over here on this side. Equals rank dot avg of the number that we want, but now it's relative to the matrix from J18 to N22, from $J $18 to $N $22. And we want to do the same ascending order. Oops, I should have a colon in here, not a comma. Okay, good, that lit up the right way. And that rank of the 2 is 1. And I'm using the autofill handle here to drag it over. And you notice it's correlated with it already. The smallest number is the smallest, biggest number is the biggest. But notice we have a 9.5 over here and a 13 in this column. So this thing is still, well, it's different from the rank order of the data. And the theory matrix isn't quite matching up yet. Now we can look at the correspondence between the two rank orders. Now we're asking, the rank of the data going to match the rank of the theory. So let's let this be equal to the correlation between the data and the theory, the ranks of the data and the ranks of the theoretical, of the entries in the theoretical matrix. And we see that correlation starts off as a pretty low 0.965 correlation, because this theory now, some of you are thinking to yourself, 0.965 is a high correlation by the standards of the oohs and ahs of correlation scales. And yes, unfortunately, correlation coefficient can be really high for a bad theory. This is the correlation between data that diverge, and this is almost a 2-to-1 interaction here. This divergence here is about 1, 2, 3, 4 plus gap over here, and it's about 1, 2 gap over here. More than 2-to-1 interaction with parallelism. It can correlate very high with the wrong data. And not only that, I published back in the 70s, 73 and 74 in the Psych Bulletin, showing that wrong theories can sometimes even have a higher correlation with the data than the absolutely correct theory if you calculate correlations using prior values like this. That you start off with some values that you think might be okay, or physical values, and you plug them into these equations using regression. You can actually find higher correlations for wrong theories than for the correct ones. Those papers are titled "The Devil Rides Again: Correlation as an Index of Fit." And then in response to explain it to some people that were confused, replied to the devil's advocates in the Psych Bullet, 1974. All right, so what we want to do now, though, is solve for values. These numbers here are just arbitrary numbers we assign to these levels of liking. Maybe there's some other levels, other values that would work better to reproduce that rank order. And so that's what we're going to try to do. We're going to use a solver in Excel to do that, to maximize this correlation coefficient. Okay, so to do the solver, you have to install the solver. The solver is sometimes found in the Excel add-ins. Usually it is, if it isn't already installed. And you can ask for it to be installed from the add-ins. So I'm going to bring up the solver here, and here comes the solver, Excel solver. And because I had clicked on this cell, it comes up over here. So we're going to try to maximize this correlation. Sometimes when you're using the solver, you want to minimize things, or you can make things equal to a particular value. You can use the solver to do that too, to solve some equations where you want a value equal. But we're going to maximize this correlation by changing cells, and we're going to change, well, I don't think we're quite ready here. Let me close out the solver and we'll bring it back up. Let me close it here. I want to make this equal to this. I'm going to force the row, because it's a symmetric matrix, all I need to do is solve for one set of values instead of two. So I'm going to have this value be equal to this one. I'm going to make this value equal to this one. I'm going to take this value and force it to be equal to this one. I'm going to take this value and make it be equal to this one. I'm going to take this value and make it be equal to this one. And then I'm going to do something else too in the solver. Because it's an interval scale, it's just an additive model. And the origin of the numbers, any additive constant I add to all the numbers, is not going to change the rank order when we add them together. And if I multiply all the numbers by a constant, that also won't change the numbers. And so that means basically we can fix two of these values to arbitrary values, and I'll just fix them to 1 and 5 for the scale values, because it doesn't really matter what we do. Or I could fix them to something so that the range of numbers somehow look the same, but I'll just fix these to 1 and 5, and we'll go from there. I'm going to fix this one to 1, and so to remind myself that I'm fixing it, I'll color it in gray. That means I only need to solve for 3 values here. And these values are going to be forced to be equal to these. So the solver is just going to try to solve for 3 numbers in this case in order to reproduce the rank order of the data. And now I think we're ready for the solver. I'll click on this cell that I want to minimize, and I bring up the solver. And so it's correctly identified the cell I want to work with. I want to maximize it. I'll click maximize. By changing these 3 numbers, I'll choose these 3 cells right there. And now we need to add some constraints to keep um, the solver from wandering off to infinity and get lost, you need to set ranges for the minimization algorithm we're going to choose. So I'm going to add the constraint because they're going to go from 1 to 5, and I know that these things are basically monotonic in this case. I know that these three scale values have to be between 1 and 5. So I'm going to add the constraint. Now we're adding constraints, and we're going to add the constraint that this number will be less than 5 and it'll be greater than 1. Then we add that this one will also be less than 5. And this one is also going to be greater than 1. And number 4 is also going to be less than 5. And it also should be greater than or equal to 1. Okay, so 19, they're less than 5 and greater than 1. 20, less than 5, greater than 1. 21, less than 5 and greater than 1. Now, normally when you're fitting numerical values, this is a good algorithm for maximizing or minimizing something. But in this case, because we are going to have changes of value that won't change the rank order, so the objective function will have flat places in it. Because we have that kind of situation with flat places, normally minimization problems or maximization problems, you try to find the slope, and if there's no slope, then you think you're at a local minimum or a local maximum. But in this case, because we're just working with rank orders, we have to choose this method right here, the evolutionary technique, and it needs these constraints here, whereas some of the others don't require maybe as many constraints. But the evolutionary technique is one that'll work when you have flat places in your objective function, the function you're trying to maximize or minimize. So I think we're ready to let the solver work, and we can click the solving method. It's got unconstrained variables are non-negative. Notice I've forced them to be between 1 and 5 anyway, so that means they'll be positive. So this isn't affecting us in this case. And I've clicked the solve, and the solution as it works, it'll be showing us how it's doing. Notice it's finding correlations of 1, but it's going to work away and see if it finds anything bigger than 1. I don't think it will. All right, it's found a solution. I can't do any better. And the correlation here is 1. And that means that the Spearman correlation between the data and the theory is 1. And that's it right here. Spearman correlation is the correlation between the ranks. And here are the ranks. Here's the correlation between the ranks. And so this shows that these data can be transformed to parallelism. These are the original data, and these are the theoretical values. If we graph these values, let me just pull them out over here. This is the theory matrix, just copied over the values. Bring down the labels and remind us what they are. We can draw a graph of these values. And you see they're parallel. And what that says is that these data can be transformed to produce these data monotonically. Let's see, what is that transformation going to look like? Well, what it's going to look like is we can plot to see, according to our idea, these are the subjective values 1, 2.7, 3.9, 4.2, and 5. Those are the subjective values of the adjectives. You can add them together, and then you need to transform them in order to get the data. And so let's see, that transformation is called the judgment function. So we can draw a graph of what the judgment function looks like. In order to do that, I need to get Excel to show me that graph. I need to string out the theory and the data. So I'm going to take the theory, we'll put that here, and we'll put the data in a string here, and we'll draw a graph of them. So we've got these values right here. It wants to take the whole thing. Let me undo that. I'm going to pay special values here. The second row. The third row. Fourth row. And the fifth row. And the data, do the same thing. We now have 25 numbers in each case. There's a lot of ties in there. And if we select all of this, we can draw the relationship between the two and ask if it's a strictly monotonic function, which we know it's going to be because the correlation was perfect here. And there's the transformation. This is the estimated judgment function. J function, which is in theory, the transformation between, on the x-axis, the theoretical value, and on the y-axis, the observed judgment. That's the bias in the response scale. Somebody might phrase it that way. So this shows that these data could be transformed to parallelism. The question of whether they should be transformed to parallelism is a separate question. Is this a correct interpretation of the data? And as I showed in 74, and again explained in more detail in my 82 chapter on controversies in psychological measurement, it is absolutely not the right thing to do, but it could be done. And this shows you how you can do it if you don't have the program Monanova, which you can actually get. It's part of the stat package that you can buy and insert here to Excel. You can get Monanova that way. But if you don't have, or you can download it as a Fortran program free from my website. So if you can run Fortran, you can also run Monanova. But here's a technique for showing how to use the solver in Excel using the evolutionary solver technique to emulate what you can do with Monanova. But should you do it? Is it the correct interpretation of the data? No, it's not. Is it a possible interpretation of the data if you didn't know anything else? Yes, it is. It's a possible theory if this was the only experiment you did. But if you do other experiments, you can show that it is not the additive model is not the correct interpretation. Additive model with a nonlinear judgment function is a possible theoretical interpretation if this is all you had, but given there are other data showing it's not the correct interpretation. So, but anyway, here's a technique for how to do it if you need to make a transformation.